Morning, guys. Okay, here's the code for the class today, MHMIQ, if you can join up to that. Okay, we'll get going. I've got the join code there for those that haven't joined yet. Okay, let's go. Let's get going. All right, so today we're going to start a new topic on trigonometry. Oops, I did not change that. 1 second. That's better. Okay. I didn't update it. Weird. Okay, just imagine that says Pythagoras and trigonometry. Okay. So there's a lot in trigonometry to get through. This course was designed just for the standard year 10 users, but you guys might actually be doing advanced, or you might be doing New South Wales 5.3, in which case there is a lot more topics in trigonometry to cover. For the 10 standard class, it is generally just a revision of year 9 trigonometry and Pythagoras. So if you're really comfortable with those two topics, I don't want to spend too long on them. We can probably move on to the harder stuff if that's what you guys would prefer to focus on. So we'll just do a few quick ones. It's basically just revision. If you're in New South Wales, you would have done Pythagoras in year 8 as well. And you wouldn't be doing Pythagoras in year 10 at all. So we can very quickly go over it if it's not something that needs to be covered. I just need to know from you guys. We don't need to know that. We're all here before. Here are the videos on the basic trigonometry topics. Eddie Wu. Okay. I did make a survey because multiple choice, because you could only choose one option. So of these things, feel free to just leave a quick note on what you'd actually like to cover today. Some of you maybe have already done this in class and you don't need to go over it. Are you able to join the class at all, Vincent? Otherwise, you can just leave a message in the chat. Okay, so trig ratios, degrees, minutes, seconds, angles of elevation and depression. Josh, if there's time at the end, I can go over some compound interest stuff with you if there's anything in particular you need me to cover. That's not the scope for the lesson today, but I'm happy to help you with it. Force diagrams and the triangle of force. That's a bit more physics-based, I guess. Oh, probability as well. Okay. Okay, so it looks like the stuff today on trig isn't really as important for you guys right at this moment. Let's just very, very quickly just go over what I've got ready, and then I can go off on a tangent and start talking about some of these other things. So that's really basic then. We don't want to do Pythagoras, let's just ignore that. Let's just go over the very basics of trig, remind ourselves what we learned last year. So here we have a triangle, all 3 sides are given. One of the angles is labeled theta. What is the value of the ratio? Opposite over adjacent. This is very, very super basic stuff, this one. Yeah, the ratio you would use is opposite over adjacent is the tan ratio. They just want the numerical value in this case. So if we have tan here, here's our opposite side. Here's our adjacent side. So opposite over adjacent is just 4 on 3. So we could even write tan theta equals 4 on 3. We don't need to solve for theta at this stage. Are you able to join in, Vincent, or not? Okay, let's go on. Looks like you're both trying to solve the ratio. Not actually necessary at this stage. The value of theta, perhaps, is what you're trying to solve. 0.023. What are we doing? Oh, 1 second, press the wrong button. Okay, we're back. All right, so how are we getting this answer? My suspicion is we are doing the wrong thing. Well, we know we're doing the wrong thing. I think one of the most important things when we're doing this as well is just make sure your calculator is in fact in degrees mode, not radians mode, because that can lead to incorrect answers. I'm just trying to work out what you guys did to get 0.023 as an answer. Hmm. What are we doing here? 53? No. The angle itself is not equal to 53 either. Unless I've done something wrong. Ah, yes, I have. I'm doing 3 on 4, not 4 on 3. My apologies. Yeah, so the angle itself would be 53, so we've gone a bit ahead of what this question's doing, so I think we're pretty right with this. Yeah, so if theta, the ratio is 4 on 3, we take the inverse tan, and we get 53 as an angle. Okay, very quickly, we'll just do this one as well. Looks like we're well on top of basic trig stuff. So cos is opposite over adjacent. No, sorry, opposite over hypotenuse. Adjacent over hypotenuse. I'm sure all you guys remember something like this to remember your ratios. So if we have cos, it equals the adjacent side over the hypotenuse. And we have adjacent, so here's theta, here's our adjacent side, here's our hypotenuse. So cos theta is adjacent, 24, over the hypotenuse, 25. And then we will take the inverse cos of that to find our answer. Which gives us, what did it want it to? Oh, by the way, cos theta with an ABC. Didn't ask for rounding or anything, which is interesting. Actually, I think for this, they probably just want this as the answer, 24 and 25. We might as well go ahead and solve it. 16 degrees to the nearest degree. Okay, moving on. Cool, we've got 3 people in now. 0. Okay, yeah. So cos theta is 0.96, yeah, and then we can take the inverse cos. Okay, let's just very quickly jump into degrees, minutes, seconds. We weren't going to cover it, planning to cover it in this lesson. Okay, so we have this conversion for, give me more digits, more digits. Let me actually just get a calculator. The one I'm using is not giving me enough decimal places to do this accurately. Is there an easy way to stop annotating? Yeah, there we go. Okay, let's go to scientific mode. Okay, so we want 24 and 25. And we want to take the inverse cos of that. Second function. What's going on? Okay, so we have 16.26, 02047, etc. So 16.26, 0204, etc. Now to turn this into degrees, minutes, and seconds, on your calculator, you'll most likely have a button that'll look something like that. We'll have the degree symbol, and then a minute symbol, and a second symbol. And now we know we have 360 degrees in a full revolution. We actually have 60 minutes in 1 degree. Like 60 minutes in an hour, we have 60 minutes in a degree. And obviously then we have 60 seconds, excuse my handwriting, in 1 minute. So if you use the button that converts it straight to degrees, minutes, seconds, it's as simple as just pressing that button and then you have it in degrees, minutes, and seconds. Most of the time you'll probably be rounding to the nearest minute. So if you look at the seconds, if you have 30 or above, it rounds up. If you have less than 30 seconds, it rounds down. So much like 0.5 rounds up, anything less than 0.5 rounds down if we're talking about decimals. When we're talking about seconds to minutes, 30 goes up, anything less than 30 goes down. Same with minutes. So if 30 have more than 30 minutes, you'd round up to the nearest degree, or you'd round up to the degree. If you have less than 30 minutes, you round down. So in this case, we have 16.26. I can see that it's going to be less than half a degree more than 16, so it's going to be less than 30 minutes. That's a sort of nice simple guideline. If you can see my calculator, one way you can actually do this, let me clear the annotations. There's my toolbar. No wonder I couldn't see it. Okay, what we can do here is actually subtract the whole number part Whoops. Go away, annotations. We can subtract the whole number part, just leaving us the decimal. And then if I times it by 60, I know there are 15 minutes. And then I have my decimal part to work out seconds. I can do the same thing again here. I can take away 15 to give me the decimal part, times it by 60, and I have my seconds. So this means that our original answer of, what was it, 16 point, I've lost it now. That was 15, wasn't it? No, 16. What question am I doing? I lost track of my numbers. Apologies for this. 16.26. Oh, I typed 15. That's all right. Oh, what happened? I've got a completely different number now. Yeah, other way. 16. Oh, what? Sorry, guys. Completely lost track of. What happened? Clear. Let's just do it again. I don't know how my 16 turned to a 15. Yep. Okay. Ah, it was when I did that originally, was it? 16. All right, minus 6. Let's just quickly do it again. Equals times 60, 15 a minute. That's right. So we get 16 degrees, 15 minutes, and 37 seconds here. We just look at the decimal part. We can see that it is 0.73. So in this case, we'd round up to 37 seconds, sorry. I know some curriculums don't require the use of seconds. You only need to know degrees and minutes, but I thought it was worth covering them both. It makes no sense to really look at one without the other. It's like, let's look at 2 decimal places, but we'll never look at 3 decimal places. It just doesn't really make sense. Okay. So that's a very quick look at degrees, minutes, seconds. We'll do a few, we can calculate them for the others as well if we'd like. Clear, go. Okay, that did not clear. All right, here's another one. In this case, we need to find the length of a side. So right angle trigonometry only really has 2 parts to it: finding a side length, finding an angle length. We always follow exactly the same procedures. Identify which angle we're being asked about or identified. So in this case, we want to find the value of x, and then hence find the value of tan theta. So to find x, we just quickly use Pythagoras. We have a right angle triangle. We know 2 of the sides. Right angle, Pythagoras says a squared plus b squared equals c squared. In this case, we already know c squared. Well, we know c, it's 13. Let's pick a to equal 5, and we don't know b squared. Looks like most of you are pretty familiar with your Pythagorean triads. You know that 5, 12, 13 is the triad, so we know x is equal to 12. If I solve this, I would get the same answer of 12. Now, hence find the value of tan theta. Now we think tan is opposite over adjacent. Tan theta then, opposite is 5. The adjacent is what we just found, which is why we had to find x first. So we know tan theta is 5 on 12. Whoa. We can now take the inverse tan of 5 on 12 to find theta. I should have just had a real calculator with me. What have we got? 5 on 12. Take the inverse tan. And something went horribly wrong. Try to shortcut to turn off annotations. Theta then equals, what's going on? I think you both all got the right answer there. 22 degrees, 37 minutes, 12. We have 22.62 degrees roughly. This is actually, we're going well beyond again. They just find the value of tan theta. If that's ever the question in a test, this is the answer here, 5 on 12. So long as you have that and you're working, if you went on and did the rest of it, there shouldn't be an issue at all. No, x definitely doesn't equal 8. You could see here, if we had a length here of 13, if this was 5, and that was 8, the only way they would ever touch each other is if they were perfectly along this line, because 8 plus 5 equals 13. So if we had a triangle with side lengths of 8, 5, and 13, it would in fact just be a straight line. Let me just quickly check on my calculator that we have the right rounding there. Clear, 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 clear. 5 on 12. Take the inverse tan, 22.6.9, yep, minus the 22 times 60. It's so much easier if you do have that degrees, minutes, seconds button. What happened there? I got a perfect 38. That seems unlikely. Oh, why did I do that? Degrees, second function, tan. Oh, yeah, okay. Yeah, it looks like that's correct. 22 degrees, 37 minutes, or 22.62 to 1 decimal place. Cool. Let's go to the next one. I just turned you off. All right, Pythagoras Theorem. I don't think we need to go over this. We're all pretty well across it. Obviously, you have your rearranged forms of the equation. Really, you just need to know this one here. If you know c squared equals a squared plus b squared, you can work all of these out. There's no point in memorizing all of them separately. I don't think I wanted to do Pythagoras, so let's skip over that. You guys, I think, are pretty well on top of your ratios. SOHCAHTOA, however you want to remember it, whether you have your acronyms. I always just remember SOHCAHTOA. Even now, I still just remember I'm using a trick. I don't actually, well, I do know them off by heart, but I still have to remind myself using an acronym. So this one here, we don't actually really need to do trigonometry. This one's really just a bit of logic. We know that tan theta equals 3 on 4. Which is equal to opposite over adjacent. But we also know that tan theta equals b, which is the opposite, over the adjacent, which is 36. So we can equate these two equations, and we just know 3 on 4 must equal b on 36. I can now rearrange and solve for b. Well, 36 on 4 is just 9. So this equals 3 times 9, 27. So no trig involved there at all. It's just knowledge of trig ratios, knowing how to rearrange equations. So this is using similar triangles. So if we had this second triangle here, which is, well, let's do that again. Let's get a different color for once. So if I had this similar triangle here, oh, that's not much better. This side here is 3, this is 4. Obviously, I can expand it out each time. Here's my new triangle, this is 8. This must be 6. And so on. I could double it, get a new triangle that has 16 and 12, always in the same ratio, 3 to 4. I could add bits now. 8 plus 16 gives me 24. 12 plus 3, sorry, where am I up to now? 8 plus 16, 12 plus 6 is 18. You can still see 18 on 24 is equal to 3 on 4. All I've done is times both bits by 6. So any similar triangle will always have the same tan ratio, and so on. Okay, next one. Clear, close, next. This one's a bit trickier, but looks like it could all be done with Pythagoras. Where did I put that one in? Yeah, we may as well do it. We've got plenty of time for now. Oh, sorry, I just noticed the chat there. Where is the link? Who's actually here now? Sorry, guys, I had the chat open, but it seemed to have fallen behind something. Oh, no. Share screen. Technology is hard. Zoom is just very counterintuitive sometimes. Chat open. Your question, Josh, about finding theta before x using trig, I'll just give people a chance to finish this question. I'll very quickly go back to that one. Whoa, sorry. Did not think that was going to change anything. So let's do this one now. Annotate. What's the shortcut? Still don't know. What is going on? Why is annotating not working anymore? That's better. All right, so x equals Yeah, so x is root 11 or 3.32. We can find y similarly. Yeah, I'll take your word for that one. And then we can just add them together to find our final answer. Or we can keep our answer like that as well, and then round that. 11.88, that seems right. 11.88, okay. I thought I'd put a trig one there. Okay, let's very quickly go back. I just want to figure out the question Josh was referring to. Which I believe was clear. Okay, it was. I believe this was the question Josh was talking about. Why wouldn't we find theta first? Well, in this particular question, I think I can see what you're getting at. This question, though, was asking for the value of tan theta, not the actual value of theta. So to find tan theta, which is opposite over adjacent, we did need to know the length of the adjacent thing, of the adjacent side. If we wanted to find theta straight away, you'd notice that we have these two sides, the hypotenuse and the opposite side, and so we would use sine. So in this case, sine theta equals opposite over hypotenuse, 5 and 13. We could solve for theta that way. Sorry. And if we solved theta that way, we could find that, and then we could use that maybe, and we could also then use tan, whatever that value was, I can't remember now. Tan theta is opposite over adjacent. And then using the known value of theta, we could rearrange to solve for x. Oops, sorry, tan. But in that case, it was just asking for the value of tan theta, not theta. So if it was just asking for theta, we wouldn't have to use tan at all. So that was a good question. Clear. I wish it would just clear when I closed it. Except for the times when I don't want it to clear when I close it. Okay, jumping back to... Oh. I could have sworn I put that in as a trig question, but no. That's just another harder Pythagoras question. I don't think we'd need to go over Pythagoras, so would you like to cover now a little bit of... oh, where's the chat gone from the start? Okay. Angles of elevation and depression. Let's go over that. I haven't got anything prepared for that. Actually, let's do this challenge question first. This is very nice. Pythagoras application. While you're thinking about this, I'm just going to very quickly get something prepared for angles of elevation and depression. Oh, I should have made that a thing. Okay, I meant to make this so you could enter answers into it, but I don't think it's going to work super quickly. And I don't want to start a new lesson and then have to get a new lesson code. So the way to think about this question, if you want, you can just pop answers into the chat for now. So we have a pole 28 meters high, and it has a vine wrapped around it, going around basically in perfect spiral up. So here we have our pole, and we can think of the vine as going around it like that. So that goes around, 7 times, sorry, I put the image slightly over it. That's definitely a 7 there. 1, 2, 3, 4, 5, let's put another one there. 7. Okay. So the pole is 28 meters high and has a constant circumference of 3 meters. So that means that for every loop, it's covered 3 meters, but it's also going up. So how can we work out the vine length here? Uh, 588 meters is very long, definitely not that long. It's longer than the height of the pole, but not by a huge amount. Okay, thank you, Rishta. We'll see you next week. So the first thing we want to think about is if we unwrapped the vine from the pole, but we kept the top of the vine at the same height, what would it look like? And unsurprisingly, we're going to end up with a right angle triangle. This is going to be 28 meters. That was the height the pole went up. It looks like Mega's got the right answer there. Actually, no, I think it would be that's not quite the right answer unless there's some rounding going on. So we know it has a constant circumference of 3 meters. And we also know that it goes around 7 times. That means this here is going to be 21 meters. The vine goes up 28 meters, and you can sort of think as its horizontal length as 21 meters. If we sort of squashed all of that down and just had it in a pile, you'd end up with just 7 loops, all of 21 meters each. So now we just have a right angle triangle, 21, 28, and x, the length of the vine, 21 squared plus 28 squared. Take the square root, and we just get an answer of 35 meters. Okay, all right, let's quickly look at some angle of elevation and depression stuff. Not hard, just takes a little bit to sort of get your head around it. Yeah, okay. Close that. Let me just pull the lesson up. Can you see the lesson on the screen? Or loading on the screen now? Slowly loading on the screen. No. Let me share it again. Okay, so angle of elevation is the easiest one. It's what you've probably generally done with all your trig triangles up until now. Angle of elevation question is something like, if I'm standing on the ground and there's an aeroplane up here, let me annotate. Let's say I've got an aeroplane and I know that the aeroplane, I don't know how I know this, but I know for some reason that the aeroplane is 200 meters away from me. And amazingly, I know that it's 14,000 meters in the air. What is the angle of elevation from me to the plane? So the angle of elevation is just the angle formed between the hypotenuse and the ground. It's easy. It's the one you basically have always looked at. It's always going to be that angle or that angle. Angle of depression is a little bit trickier because it's going to be this angle here, not this angle. So if angle of depression, same situation, there's a plane in the air. I'm down here. What is the angle of depression from the plane to me? Now, in that case, I can't just draw this triangle. Oh, actually I can. In this case, the angle of depression from the plane is the angle of elevation from me to the plane. That's because if we have parallel lines, any line that cuts across it is going to make two equal angles on alternate sides of the line. So in this case, we have these, and yeah. So we know that this angle of elevation is equal to the angle of depression. Most common mistake is people are going to work out this angle for the angle of depression when it is this angle here. So that's really the trick to angle of depression. They're generally just a little bit harder than normal trig questions because it just takes a little bit of thinking about the language being used. Most trig questions are just a diagram. You don't need to think. You've got the contextual ones you need to think about. In this case, angles of elevation and depression, there's always some sort of context going on. So you can see here, if you have the direct distance between the 2 points, you've got your horizontal plane and your vertical plane. Let's try this question. Just pop your answers in the chat, guys. Why do I keep pressing that stop share button? It's so tempting to press. Big and red. So solve for x, the angle of depression. They've colored in two angles here. This one, remember, is not the angle of depression. Our angle of depression is going to be this green one here with the two rings. So let's think about what ratios we need and what else we actually need to add. So if this is 7, that's 7. We don't know the height, but that's okay. Let's use the two things we do know. If this is x up here, remember this is also x here. So we could just work out the angle of elevation and pretend that we worked out the angle of depression. So we have hypotenuse and we have adjacent. So we're going to use cos. So I know that cos x is equal to adjacent 7 over the hypotenuse. And we can take the inverse because of that. And then we want to solve that. I don't have my calculator. I really just should have grabbed one. I will trust that 68 is correct. Looks correct. Why, chat? Why you be so chatty? 7 divided by 19. Take the inverse cos. Yeah, and we'll get 68.38 degrees. They wanted 2 decimal places, so 68.38 should do it. Perfect. Okay, so that's just a really simple one. Basically, it's just a matter of turning an angle of depression question into a normal trig question. So it's just about getting the language right, making sure you fully understand the point of reference, whether it's the angle from the bystander to the object or whatever that object is. Okay, let's have a go at this one. The ones with the diagrams obviously are going to be a bit easier because you've got a bit of context already there. The worded ones where you have to draw your own diagram, and they're a bit trickier. Okay, so the top of the lighthouse is X meters above sea level. Find X, correct to 2 decimal places. So in this one, we're given the angle of elevation. It basically just becomes a very straightforward trig question again. We know that the angle of elevation of the top of the lighthouse from Lucy is 11 degrees. Lucy's on the ship. So we know this is 11 degrees. The base of the cliff is 576 meters away. So it's all just about interpreting the worded sentence and transcribing that information onto the diagram you have. So now I have an angle, I have a side, and I have an unknown side. I've got my opposite side, and I've got my adjacent side. So I'm going to use tan, which is opposite over adjacent. We know tan 11 then must equal X over 576. Once again, we just, this one, we went rearrange. So let's times both sides by 576. And then we can just solve that. Tan 11, about 0.19, times that by 576. Now, before we get an answer, it's always wise to just have a quick approximation. This is 11 degrees, this is 90. So this is 11, this is 90. This is clearly going to be more than 11. And if you recall, the bigger the angle, the longer the side opposite it. The hypotenuse has to be the largest angle, so this is always the longest side. This angle is smaller than this angle, so X has to be less than 576. So if you did something and got an answer bigger than 576, we know we've gone horribly wrong. Quick ballpark figure, if this is 11, it's going to be maybe a quarter, a fifth of 576, somewhere around that much. And we're getting an answer of X is equal, how do they want to 2 decimal places, 111.96. That's around about a fifth of that. Obviously, if this is 45, this is 45, these two lengths have to be the same. You might have seen a unit triangle before. This is, oh, I did that really bad. Clear. We'll look at unit triangles in another lesson. But if I have an equilateral triangle of side length 1, let's say side length 2. They're all side length 2, and I cut it in half. I'm now left with this triangle here, where this is 60, this is 30, 90, 2, 1, because this is half of 2. And then if I use Pythagoras, I can find out the other side length. And I get a side length of √3. And so from that, we have our basic trig ratios. This is what you'll learn in advance. I don't think the general Year 10 course covers these unit triangles, but it gives us basic ratios. So tan 60, tan opposite over adjacent, tan 60 is equal to √3. Tan 30 is equal to opposite over adjacent, 1 on √3. You can see cos 30, cos adjacent over hypotenuse gives us √3. It's easy using my mouse. √3 on 2. We know, well, you might remember, cos theta equals sine 90 minus theta. So that means sine 60 also equals √3 on 2. That's because the so if you have cos 30, opposite over hypotenuse. If I have sine 60, I have opposite over hypotenuse. Sorry, if I have sine 60, I have adjacent. So no. Cos, I have adjacent over hypotenuse, √3 on 2. Sine 60, I have opposite, which is my same √3 over 2. And then you can see sine 30 equals sine opposite over hypotenuse. I have 1 on 2 is a half, which is also cos 60. So these are sort of basic identities that you'll need to know later on once we're doing stuff. You don't need to know it just yet. Let's quickly finish this question up. If the lighthouse is 30 meters tall, how tall is the cliff? Well, now we know a bit more about it. We can add some stuff to our diagram. So let's just quickly whip up a new diagram. X is 111.96. We know this is 576. Oh, the lighthouse is 30 meters tall. That's very easy. Now we're just adding 30 to 111.196. No. Oh, what? Oh, how tall is the cliff? Oh, minus 30, sorry. Bad diagram. So we were working out the angle of elevation at the top of the lighthouse. So we want to take away the 30. My mistake. $81.96. Correct. Chat. Okay, 81.96. Perfect. Mega. Let's not do that one. Okay. Last 5 minutes. Does anyone want any more on angles of elevation and depression right now, or is there just a random topic you would like me to cover? Why has it got there all the time? Let's do this one in the meantime if we have no other things we want to cover. Force diagrams and the triangle of forces. What topic are you actually doing that in, Josh? Ashes. Oh, are you in senior? I haven't done force diagrams for quite a long time. I'd have to very quickly brush up on it myself. Not really the focus of this year 10 class, so I think I'll just leave that for the moment. I can help you at some other stage if you'd like. Yeah, no, it is related to the trigonometry. You'll be using the sine rule, I believe, to work out how to figure them out. Has anyone here covered the sine rule at all? I don't think we have anything ourselves on force diagrams. No. Okay. Tree diagrams. Okay. Not sure exactly what of the force diagram stuff you need to know, so I'm not really sure how to cover it. But generally, you'll be using the sine rule. Which works for any triangles. So if I have a triangle here, triangle ABC, and side lengths A, B, C, the ratio of the sine of the, so sine A over A has to equal sine B over B. Let me very, very quickly just cover a case of that. What do I want from? I need an advanced. So 5.3. If you can stay back a little bit, Mega, I'm happy to very quickly go over tree diagrams with you as well. So the sine rule is used in the cases where you have clear, where you know either two side lengths and an angle, and you want to work out the other side length, or you have two angles and a side length, and you want to work out the other side length. And I believe you'll be using that in your force diagrams, because generally you'll have maybe a vector like this and a vector like this, and we need to work out this one here. So very similar setup. Let's say that's C, that's A, and this is B. Sorry, I can't actually help a bit more with this, Josh. It's not a topic I've taught at all recently. So I really would have to brush up on it quite a lot. So trying to keep it within the realms of trigonometry that we're doing here. Feel free to email me about it, Josh, and I can help with you there. So a question like this, let's just very quickly do this one. So here we have two angles, a side length, and we want to know the other side length. So we can just set up a very simple ratio, sine 107 over 68. So if you have an angle and the side opposite it, it must equal the sine of the other angle over its side. And I can just very quickly rearrange this now. Cross multiplying. Divided by sine 107. Whoops, that's not what I said. Suppose I should do that. Calculator. Should give us degrees, hopefully 34. Wait, 34 point. What do they want? Right, your answer to 2 decimal places, 38.47, should get us the answer. Whoops, that's not what I wrote at all. 38.47. No. What have I done? $34.47. Oh, yes, sorry. I wrote 34. I said 38, but I meant to write 34. Okay, that's a very, very basic sine rule question. Not sure if you've also learned it, Josh. You will have. You've got the cos rule and then a variant of Pythagoras for non-right angle triangles. We'll be covering all that next week. I might just very quickly go over tree diagrams, so feel free to listen in, Josh, or you can drop out of it. That's fine. Thanks for coming this week. Hopefully see you next week. You guys might all be back at school next week. I'm not sure about that, so we'll see what the numbers are like. Probability. Tree diagrams. Is there anything in particular about them, Mega, that you're not sure of that you want me to go over? Or is it just the general how to do them? Non-replacement, okay, yep. So this is a very, very simple example. Obviously, there's no replacement here. Yeah. This is a very weird example though. This probability that a set of traffic lights is equally likely. What's the probability that both sets of traffic lights will be red? For this one, you've got the tree diagram. It's just a matter of counting the outcomes that have 2 reds, which is just this one here. There's only one outcome. There were 9 in total. Very simple one. Whoops. Now, within Mathspace, we don't have the best way of creating your own tree diagrams. So most of these are already drawn out. Was there a specific question that you have in mind, Mega? I can just go over that with you. Here's a tree diagram one. Let's do this one. Here's a create one. Okay. This is a very, very simple one. Obviously, the captain can be any one of these 3 people. This is without replacement. So obviously, if Matt's the captain, he can't be the vice captain. So our only options there are Rebecca and Helen. Same here, Matt, Helen, Rebecca, Matt. Very, very simple. That probably wasn't what you're after. Okay, here's a good one. Let's just go to the hardest one in the set. Okay, so Michelle has 3 chances to win a race, has 3 races to swim at a swimming carnival. The chance she wins the first is 0.7, and if she wins, her chance of winning the second is 0.8, but if she loses, her chance of winning in the second is 0.4. So let's just draw that so far. So chances of winning the first one, 0.7. Her chance of winning the second is 0.8. If she wins, if she loses, her chance of winning the second is, okay, yeah. So this has to be 0.2 for losing her second. This must be 0.3 then. These events are complementary. They must add up to 1. And then if she loses, then her chance of winning the second is just 0.4. Which means she has 0.4 0.6 chance of losing the second race if she loses. If she wins the first two, oh, there's a third layer, then her chance of winning the third is 0.9. I'm going to use the annotation tool because it works so much better than the Mathspace tool. If she lost the first two, then her chance of losing the third is 0.9, which means a win is 0.1. And if she won only one of the first two, her chance of winning the third is 0.6. So that's this case here, a win and a loss, 0.6 for a win, 0.4 for a loss. I did not give myself enough room to do this. And so this is the other case where she wins one of her first two. So this must be 0.6 for a win, 0.4 for a loss. So it's not the neatest tree diagram I've done. Calculate the probability that Rochelle won all three races. Okay, so now we have a tree diagram. We can just look off the case of her winning all three. And so the probability of her winning her first was 0.7. Probability of winning the second is 0.8. Probability of winning the third is 0.9. There's our answer. And that gives us, oh, where am I? Yeah. 0.504. It's 3 decimal places, yeah. Calculate the probability Rochelle won the third race. Okay, so in that case, we just need to look at the last branches. She won here, she won here, here, here. These aren't equally branched. If these are all equal, we could just count the number of cases divided by the total number, but we will actually have to crunch the numbers of each one. 0.7 times 0.8. No, is that right? Oh. Yeah, there's our probability tree. We did that. Yeah, so we do have to figure out each one. So there's a very good chance that she won all of them. We already worked that one out, so we don't need to work it out. This one here, win, loss, win, 0.7 times 0.2 times 0.6. There were 4 cases she won her last race in total. We need to work this path out. 0.3 times 0.6 times 0.6, sorry, 0.4, that one. And then this last path here, 0.3 times 0.6 times 0.1. Yep. Was not a solid tick because I already worked that one out. They weren't expecting me to do that. And that gives us 0.6708. 6780, sorry. Let's write that as a percent. We should get away with that. No. Oh, it doesn't want it as a percent. That's a bit mean. I guess it does say the 3 decimal places. Okay. Okay, looks like you've been it's a shame, Josh. Yeah, we're going to be discussing what to do with Mathspace Academy in the future. Obviously, with everyone going back to school, it's going to be less useful to be running them at school time. So we're looking at maybe making some videos for topics that you can just watch at your own leisure. But thank you for that feedback. It makes it worthwhile for us doing it, knowing that you guys are actually getting a lot out of it in this trying time. So feel free, if you have questions, about anything at any time, email me. If I'm not busy, I'm more than happy to help you guys out. We're here to help you guys learn maths and enjoy maths and be better at it. So I'm more than willing to give up time whenever is appropriate to help you guys with stuff. Okay, thanks guys. Enjoy your week.